So let us take product of two insertions. Let us take the case of product of two insertions, say xt and xt prime. You are inserting two x's at two different times. So from the path integral language, you would be writing dx e to the power I by h bar s of x excuse me. You would be writing dx e to the power I by h bar s of x, and this is the insertion. And the question is that what is the corresponding expression using matrix mechanics language? And there you must be writing something like x at t prime I. However, you encounter right away, you encounter a problem here. If you want to equate these two, then there is a problem here, because here it doesn't matter whether it is xt prime or xt prime xt. The ordering of these two does not matter, but it does matter here. How? What are you actually calculating when you are inserting xt prime? Whether you are calculating this one or xt prime xt, which one are you calculating is something that needs to be figured out. Okay. So since these are classical, so the point is that these are classical functions, and therefore ordering does not matter. Here, ordering matters. Now, to resolve is actually it's not that difficult a question. To resolve this, you could again cut open and sew back the path integral. So let us look at this picture here. So you have this in path integral, but two operators are inserted at two intermediate times, t and well, it could be, yeah, two intermediate times. Let me not name them at this point. So at these two different times, you would cut open the path integral at two different times here. And we know from our already we understand how to interpret such pictures in terms of matrix mechanics. So as time is evolving this way, this is your initial time, this is the final time, and therefore the levels at which you are cutting it open, they are telling you, that is telling you the ordering at which. So if t is greater than t prime, then your picture is this, and in that case the operator ordering will be x hat t, which is at a later time, x hat t t prime. This is the ordering that should sit here, because this tells you a particular ordering, ti, then t prime, then t, and then tf, right? So this is your ti and this is your tf. So that's a particular ordering, ti, t prime, t, and tf. If it would be the other way, if it would be, say, if this will be t prime and this will be t, then your ordering will be x hat t prime, x hat t. So it depends on whether t is greater than t prime or t prime is greater than t. The ordering depends on that. Okay, so the ordering depends on whether t is greater than t prime or t prime is greater than t. Whichever is higher time will be sitting on the left of the factor at lower time. That is the point. So therefore, that is the picture here. So therefore, we should write this expression, that integral dx I to f to the power I by h bar s I f x xt prime should be equal to f. So if t is greater than t prime, so let me put theta t minus t prime, then this term will be in the right one, xt x hat t prime. If it will be t prime that is greater than t, then it will be x hat t prime x hat t. That is the result, and this is called time order product of x hat t, x hat t prime. Time order product means that whichever time is greater sits on the left. Okay. And its explicit expression is given by this one. So this is therefore, since this picture is quite general here, this cutting open and sewing it back, and this and the ordering with respect to the initial and final time tells you that it's a general result. So in general, the statement would be so in general, path integral computes expectation values of time ordered product of operators. So this capital T here shows that this product is time ordered. Okay. Now, next point that I would like to discuss is operator equation of motion So in the usual quantization equation of motion, so in the classical mechanics you have a classical equation of motion, and then when you quantize, then the equation of motion is described by what is called Heisenberg equation of motion. And Heisenberg equation of motion is usually written in terms of phase space variables, but then you can convert it to a configuration space variables. And so you can write an equation involving x operator and its time derivatives, which is same as the which is an operator equation, but its form is same as the classical equation of motion. And so this written in terms of configuration space variables, both these two frameworks like matrix mechanics and path integral should give the same result. That is what is expected. And let us check that. We shall check that. We shall spend some time on with this calculation. So the statement is in matrix mechanics, one obtains operator equations by writing Heisenberg equation of motion in terms of configuration space variables. Once that is done, then that can be compared with the path integral statements. So such equations should be so such equations should be true in both the also in path integral statement. So when we write down these equations in terms of configuration space variables, then it becomes comparable to corresponding path integral statements. Then these equations become comparable to path integral statements. Quantum mechanically, subtlety arises. Quantum mechanically, subtlety arises when there are coincident operators. All these results results should be in agreement in both the framework. So let us take an example and demonstrate how this is happening, how this can happen.